Hello and welcome to Physics Ka Doctor. This is Dr. Ghanshyam Tejani and let's start session number 5 Elastic Potential Energy. This is chapter number 9 Mechanical Properties of Solid and in the NEET JEE unit number 7 Properties of Bulk Matter. And with this chapter number 9, this is our session number 5. We studied various examples on tensile stress, compressive stress, and the bulk modulus, right? And here we have elastic potential energy. This session it is dedicated fully to the elastic potential energy. So in the mechanical properties, whenever we compress a body, say for example, this is a spring. We all have spring with us, right? So when we compress the spring, what happens? It is an elastic property, so it compresses. You know that elasticity. What is meant elasticity definition? A property of material which regain its shape and size after removal of deforming force. Similar is applicable here also when the spring at its normal state, if we expand, if we apply some force, so what happens? There is an increase of length. Definitely there is an increase of length. Yes or no? Right. See, and when we expand this spring, so definitely there is some energy stored inside this spring. And because of that, when we release this spring, what happened? It return to its original shape and size. So when we deform any body, that means a body is subjected to some storing of energy. Body stores some energy. Right. Similar case is applicable when a body it is compressed. There is a decrease, but once we release this deforming force, what happened? It regain it return to its original shape. And therefore this body it's contains some energy, and we need to study this is called strain energy. It is also called potential energy. The potential energy doesn't only for the virtue of height, but it is also in the virtue of deformation, right? So energy stored in a strained wire or in a spring, that is known as strain energy. It is also known as potential energy. So if a wire is stretched, the potential stored per unit volume is given by energy stored per unit volume. Energy stored per unit volume is equal to 1 half stress multiplied by strain. 1 half stress multiplied by strain. You remember this definition, just remember this definition. Can we put store energy? Total energy is U, volume is V, stress sigma, strain epsilon. It is very well known phenomena, right? So stored energy volume 1 half stress, we can put in the value of stress F by A. Strain we can put small l, or sometimes it is also used as a delta L, either small l or delta L. So these equations will be useful. We will learn few more equations also. These equations are useful. This part, which is a potential energy, or we can say strain energy. So let us have elastopotential energy, or we can say strain energy, or only potential energy of a spring. Example number 1, a wire of length L is stretched by a length L. When a force F is applied at one end, if the elastic limit is not exceeded, the amount of energy stored in the wire is given by. So say for example, this is our wire which is applied some force F, and because of that there is a increase of length. Because of that there is a, say for example, increase of length. This length is increases L, small l, and the original length is L. Original length is L. So we know that in the stretching of wire, we can consider as a work done against internal resisting force is stored elastic potential energy. So this is given by energy stored divided by volume is equal to 1 half stress by strain. So we can put stress F by A, strain L by L, small l by capital L. And what is volume? Volume of this body is area multiplied by length. So we can put area multiplied by length, area and length we may cancel out this, so it become 1 half FL. It become 1 half FL. So whatever force is applied and change of length, that gives us energy stored. That gives us energy stored. See, it is also known as work done. What is work done? Force divided by displacement or distance traveled. So here displacement we consider as a delta L, force multiplied by delta L. So we can solve by that also work done. It is so simple like that, isn't it? One more example from NEET, directly from NEET. When a block of mass m is suspended by a long wire length L, the length of the wire becomes L plus small l. The elastic potential energy in the extended wire is. We need to find out now elastic potential energy stored in the wire. What is that? So this is original length is L. When this mass is attached, so it become some expansion in the length. So it become L plus small l. See, some small l, either you can use small l or we can use delta L, whatever as per given we can require. So answers are there. Potential energy mgl, 1 half mgl, 1 half mgl, capital L mgl. NEET 2019 the question was asked in the NEET 1919. Wow. So in stretching a wire, the work done against internal storing force. What is elastic potential energy? Energy stored divided by volume is equal to 1 half stress multiplied by strain. What is stress? 1 half F by A. What is F? mg, m by g, and L is here given. Capital is given, small is given. So it becomes 1 half mgl, 1 half mgl. Solution is 1 half mgl. See, or we can also solve by using this method. See, work done is equal to what? Force multiplied by change in length. We have seen during theory part or during example number 1, work done is equal to force, 1 half force multiplied by change of length. What is force? F. mg, change of length, small l, so it becomes 1 half mgl. What is our solution? 1 half mgl, but this b. 1 half mgl, not capital G. Capital G is a different thing. So our answer is B. Let's have example number 3. Again, see, potential energy, the equations are very similar and methods are also very simple. Don't let it go. Example number 3, a wire fixed at the upper end stretched by L by applying force F. Very similar question to the top. To the question, example number 2, the work done in the stretch A, F by 2L, FL to FL, FL by 2. JEE 2004, the question was asked. So we know that stretching in the wire against internal restoring force is stored in elastic potential. So energy stored divided by volume per unit volume is equal to 1 half stress multiplied by strain. What is stress? 1 half F by A. And you can put this volume AL, volume AL. This will be cancel out. This is capital L, this is capital L, right? FL, or we can find work done is equal to W, 1 half force multiplied by change in length. So force is equal to FL and that become 1 half FL, 1 half FL, 1 half FL or FL by 2. Answer number D is the correct answer. Answer number D is the correct answer. Very similar to question number 2. There is no big difference here. Shall we go to next? Yes. Example number 4. When a force is applied at one of an elastic wire, it produces a strain in the wire. Why? What is why? Young's modulus. Why is Young's modulus of the material of the wire? The amount of energy stored per unit volume in the wire is given by. What is the solution? So we know that energy stored divided volume is equal to 1 half stress strain. Put the values 1 half sigma epsilon. Now see what? Can we put sigma is equal to YE? Can we put sigma is equal to YE? Yes, of course. We know that sigma is equal to YE epsilon, sorry, not E. Put this value here, so it become 1 half epsilon square. 1 half epsilon square. So it is asking amount of energy stored per unit volume of the wire is given by. So you can have this value, or you can put values of epsilon. Whatever option is asked in the examination, you need to perform in this manner. We have one more, JEE 2005. We got another question from JEE 2005. If capital S is stress and capital Y is young modulus of the material of a wire, energy stored per unit volume. So what is equation of energy stored per unit volume? Is 1 half stress multiplied by strain. What is stress? We know it as sigma, but here we will consider as S. What is strain? Epsilon. So 1 half sigma epsilon. See, we need here the answer in terms of sigma. So we need to put value of epsilon here. So sigma is equal to y epsilon. Can we put epsilon is equal to sigma by y? Yes, put this value here. So it becomes sigma square divided by 2y. And what is sigma? Sigma is s. So let's see what is the solution. Sigma square divided by 2y, s square divided by 2y. Is it B solution? Yes, answer number B is our correct answer. We have one more example number 6. A wire of length L, cross section area A is made of material young modulus Y. The work done in the stretching the wire is amount X is given by. And the similar kind of question was asked in IIT JEE 1987. Options are also given YAX square. See, as per requirement of option, we need to derive solution. So energy stored by volume is equal to 1 half stress multiplied by strain, or you can take potential energy direct work done. You can also take stress sigma epsilon. We can put sigma is equal to YE. So it become sigma Y multiplied by epsilon square. Epsilon is equal to change of length. That means here x is given divided by original length. So put here x by L square, and the what is volume? Volume is AL, so it will go opposite side. So you can put out this, you can remove this. So what is solution? What is solution for that? Y A x square divided by 2L. Is it B? Y A x square by 2L. Yes, solution is B. Solution is B. What next? Are we going to the next example? Yes or no? Example number 7. A wire suspended vertically from one end. Wire, let's do a wire which is suspended vertically. Consider this is a straight. A wire suspended vertically from one end is stretched by attaching a weight 20 newtons. So suppose on the same wire some weight is attached, 20 newton weight is attached. The lower end the weight stretch, and this change it is 1 millimeter. How much energy gained by the wire? So we know that F is given 20 newton. Delta L change of length is given 1 millimeter. We may convert this into meter. 0.001 millimeter. 1 meter is equal to 1000 millimeter. So that means 1 by 1000 meter equal to 1 millimeter. We know this all. So we know that energy stored by volume is equal to 1 half stress by strain. Let's put these values here. So stress is equal to F by A, strain is equal to delta L by L. Also we can find energy stored is equal to work done, force multiplied by change of length. Both are same. Right? You can take volume on the opposite side, so it become A, L. AL will be cancelled, so it become similar answer. Right? Either you go with work done or stored energy per unit volume, whatever. Force is given 20, yes. L is given 0.01. Yeah, answer we got 0.01. 2 cancel out. Can take this. Worked 0.01 Newton meter, 0.01 joule. Which one is correct? Answer number A is the correct answer. Answer number A is the correct answer. Yeah, it's a great pleasure to have this answer. So we have example number 8 and it is from JEE 2003. A wire suspended vertically from one of its end is stretched by attaching a weight of 200 Newton to the lower end. Very similar question. The wire suspended vertically from one end, its stretch by 200 Newton is so delta L is equal to 1 millimeter. You can convert this into meter. And what is energy stored in this? So F is 200 Newton, delta L is 1 millimeter. You can convert this into that. And JEE 2003, the question was asked. So energy stored by volume is equal to 1 half stress multiplied by strain. Similar question, similar. Just put value of F and delta L. So answer is that 0.1 joule. Answer is D is the correct. See, example number 7 and 8 both are identical, only the difference was 20 Newton and 200 Newton, nothing else. Very similar question was asked in JEE 2003 also. Now we have another question, example number 9. A uniform steel wire of length 4 meter and area of cross section 3 multiplied by 10 power minus 6 meter square is extended by 1 millimeter by the application of force. If the Young modulus of steel is given 2 multiplied by 10 power 11 Newton per meter square, the energy stored in the wire is 0.025 joule, 0.050 joule, 0.075 joule, 0.100 joule. The given is that uniform steel wire of length 4 meter. Maybe given, say for example, this is uniform wire 4 meter length. And the area of cross section is 3 multiplied by this is area is given. L is given. Extended by what is the increase of length is given 1 millimeter because of the force which is applied, right? Because of some force is applied. If the Young modulus of steel is 2 multiplied by 10 power 11. Okay, fine. So equation L is given 4 meter, area is given 3 multiplied by 10 power minus 6 meter square, delta L is given 0.001 meter, Young modulus Y is equal to 2 multiplied by 10 power 11. Fine. We have energy stored is equal to 1 half strain multiplied by stress. So we can put these values here and it's stored W work done force 1 half force multiplied by delta L. We have this equation sigma is equal to F by A, epsilon is equal to delta L by L, sigma is equal to, we can put these values here, whatever it is required. So we can find F, A, Y, delta L. Put this value here. Put this value here, F. So W become 1 half A, Y, delta L square. Putting this all the values here, you can cancel out this 2 and so it becomes 0.075 joule. It becomes 0.075 joule. Our answer number C is the correct answer. Answer number C that become correct answer. So we have example number 10. What is given? A boy's catapult. See what is catapult? This is the catapult. Yeah. Catapult, you may not know all the things. If sometime you don't know, then ignore that part. From the other data, you will understand what exactly requirement. A boy's catapult is made of rubber cord, which is 42 centimeter long. So this length, entire cord length is given 42 centimeter with 6 mm diameter. The diameter of this is given 6 mm. Cross section of negligible mass. So we are not considering mass of this catapult rubber. Then what? A boy keeps a stone. A boy keeps a stone weighing 0.02 kilogram on it. So boy is putting weight somewhere here. Mass is given 0.02 kilogram on it and stretches the cord by 0.02 centimeter. So we can write is a delta L. By applying a constant force when the release, the stone flies off with velocity. With it flies velocity v is equal to 20 meter per second. Neglect the change in the area of cross section of the cord while stretch. The Young's modulus of rubber is close. So Young's modulus we need to find capital Y. Oh wow. Excellent question. Again, let's repeat all the things. So see first the boy's catapult. So this is known as catapults is made of rubber cord and the length is given. This is length is given. So first is L 42 centimeter is given. We can convert this into meter. So we know that 1 meter is equal to 100 centimeter and the reverse is also true. With 6 diameter, we may convert. So diameter of this cord is given 6 millimeter. So diameter is given d 6 millimeter. We can convert this into meter also. So 1 meter is equal to 1000 millimeter. Then the boy keeps a stone. So here there is a stone of mass 0.02 kilogram and stretch. So there is an increase in length. There is a delta L 0.2 centimeter. And because of that, the stone receives velocity 20 meter per second. And what is Young modulus Y? Excellent question, don't you think so? Excellent question it is asked. So we know that energy stored is equal to 1 of stress multiplied by strain. So we can have the same equation F by 8 delta L by L. And we can get the energy stored by using this equation. Isn't it new equation? No, it is not new equation. W 1 of F delta L. We did this previously also. And we know that space strain relations are also available for all of F by A is equal to Y, and we can put the value of F is equal to energy stored in the rubber. Right. So here it is component is important. Right. The energy stored, whatever it is stretching, because of that energy stored, we will assume that total energy will be given to this stone. So energy stored is equal to 1 of F multiplied by delta L. We know that from here, right? Energy stored is equal to 1 of F delta L is equal to energy gained by this stone. So it become volume. So we know that potential energy is equal to 1 of mv square. So it become 1 of Fl equal to 1 of mv square. Put the values here, nothing else. Now F is equal to Ya delta L by L. Opposite side 1 of mv square. Put all the values here and you will have a solution. Y is equal to 3 multiplied by 10 power 6. So approximate solution is 10 power 6 Newton per meter square. So value is 10 power 6. Answer is A. Sometimes it looks difficult, but actually it is not. If you studied properly, then it won't be a difficult, right? Here only the component which is to remember here it is energy stored in the rubber is equal to energy stored after release. Thank you very much for watching Physics Doctor.